Anyway, good evening to you, Somnath. I have a very pleasant duty of introducing you, and I'm extremely happy to do that. I think for the benefit of all who are here, you all know Mr. Somnath, particularly what happened on 23rd August this year. I think it was a very historic journey for the Chandrayaan-3, which positioned our Vikram lander very successfully on the southern side of the moon, which really brought glory to the country and brought glory to ISRO and all that. So that distinguished personality is with us here today. In fact, because of that, I think now everybody knows Somnath. I don't think we need to really introduce him anymore, but I think formality demands that I should really give some of the things because many of them may not know that. I think he took over as the chairman ISRO on 14 January 2022. And presently he is not only chairman ISRO, chairman Space Commission, as well as secretary Department of Sports, all three responsibilities in one. And in fact, technically, he is one of the experts in the structural dynamics and control, dynamic analysis of separation mechanism, vibration, acoustic testing, launch vehicle design, and launch services management. In fact, before taking over as chairman ISRO in January 2022, he has held several responsibilities, a plethora of responsibilities, starting from project director, GSLV Mark III. I think you all know that that is the vehicle which really carried Chandrayaan-3 and created history. And also, I would like to tell that it is to the credit of Somanath that since the inception of Mark III as operational, 7 launches out of 7 have been successful. It's one of the very major milestones as far as the ISRO is concerned and India is concerned. And of course, he also headed the Liquid Propulsion System Center. Of course, many things have been done. I would like to highlight a couple of them. One is the cryogenic engine development, which is one of the very critical items which have been successfully flown in the cryo stage of Mark III first flight. Then, of course, the very prestigious Vikram Sarabhai Space Center he headed for more than 3-4 years. And again, he is deeply involved in the critical development of the Gaganyaan system, which is slated for launch within the next 1 year. And also, you might have heard the small satellite launch vehicle is again very successfully done. And again, many other technology elements like reusable launch vehicle, air breathing, many of them have been done. And of course, the Gaganyaan is the next step that is really being prepared. And under his dynamic leadership, I'm sure that you will also hear the success story in Gaganyaan as and when it happens, just like the country enjoyed the success of Chandrayaan-3. Of course, he is a fellow of several academies like INAE and National Academy of Sciences, and also he was the member of the International Academy of Astronautics at Paris. Of course, I don't want to get into the list of his awards because then I think I'm going to eat away in his time. He has a number of awards for his credit. With these few words, let me welcome you and look forward for your lecture now. So over to you, Somnath.
Thank you, Dr. Suresh, for that introduction. I'm really honored to hear it from you, especially the community of INAE who are assembled there for their annual convention. And thank you for the opportunity given to me to speak today, though I couldn't physically be there. Sorry that I couldn't come, but then this online possibility is really encouraging for all of us. So let me go to my talk. It is all on Chandrayaan-3. I think many of you know well this whole all of this. But then what is most important is what has shaped this and what is the outcome is something that I would like to discuss very quickly because it's an evening talk. And I believe that you don't want it to be loaded with too much of technicalities. So I thought that I will make it very simple and for enjoyable to you. So before I go, let me just try to make it share and then see whether it comes and confirm that it comes. I hope that it is visible there. If somebody can confirm, it will be very nice.
Yes, sir. Yes, sir.
Okay, fine. Thank you. Thank you once again, and I would like to present the mission to the moon and the outcome that has been hailed as one of the historic event in the recent times in space activities. And we are very proud of this fact that the Chandrayaan-3 could do the soft landing, but it's not an accident. I think that is something that we need to understand. It is a work of many years of work leading from the Chandrayaan-1 to Chandrayaan-3, and how that contributed to the success in Chandrayaan-3 is something which I would like to highlight today. This vision of exploring moon has been one of the things which we started many years back, way back in 2005-7 time frame. And Chandrayaan-1, we could do it at that time with the PSLV, which was a very game changer at that time, because it was only an orbital mission, but with an impact probe as well. And Chandrayaan-2, Chandrayaan-2 was a full-fledged orbiter and lander and rover with its experiment suite in both in remote sensing and in situ measurements. And Chandrayaan-3 was a repeat of that, with, of course, with certain changes which I will be highlighting. It's a series of activities in exploring moon that resulted in successful landing today. And of course, it opened a way for future exploration of moon. And the announcement by our Honorable Prime Minister, you would have heard that he wants an Indian to land on the moon by 2040. I believe that this is going to be a continuous series of developing capability in space capability for enabling such a thing to happen. So it cannot happen all on a sudden. It has to happen on very calibrated, very measured steps that has to taken from now to that point. Now going back to Chandrayaan-1, it has been one of the important mission where it made history by finding the presence of water molecules on the moon. I think this aspect is also well aware of. And when this mission was conceived, I think we must all remember that the launch capability that we had was only of PSLV. So the whole credit goes to the team who to engineered such a craft, Chandrayaan-1, to go to moon and have an orbital mission and do some useful scientific experiments with the capacity available in PSLV. And that is very important, how that mission was conceived and executed. I think the input that is derived from that mission helped us to plan future missions using in Chandrayaan-2 and Chandrayaan-3 as well. There were almost 180 plus scientific publications that came out of it. And the most important being the one which we all know, the presence of water molecules on moon. And it was not only that we had also payloads, not from India, but from other nations, Europe and US as well. And some of the US payloads were very important in terms of identification of the presence of hydroxyl molecules, later were confirmed using Indian payloads as well. So this is something which is very unique. And of course, in the Chandrayaan mission, one mission, there was another element called the Moon Impact Probe. This was introduced towards the last phase of this mission. And it wanted to have a hardware that goes up to the moon surface and land on it. Though it was an impact, not a controlled entry, but it also did a very, very excellent scientific outcome during its short journey of traveling from an orbit of moon to the surface of the moon where it impacted. So, the first hardware that reached on the moon happened to be the Chandrayaan-1 Moon Impact Probe, which had its very camera systems and instruments to measure the specific parameters while it was traveling towards the moon. So this is the history of Chandrayaan-1. But when you look at Chandrayaan-2, I can tell you that Chandrayaan-2 was the mission, though it had the last minute problem of not able to make that soft landing. It helped in a big manner to achieve this in Chandrayaan-3. That part is something which we should understand. Of course, while Chandrayaan-2 was being planned, we had the opportunity to use the first ever LVM-3, the first operational mission was available. So after the development flight, when this was available, we had taken a calculated decision at that point in time to have this mission, most prestigious mission, the first ever operational mission of the launch vehicle Mark III. That again is a very commendable decision that we must appreciate. This allowed us to have the engineering, the whole craft in a size and envelope. There are many changes that we could do because of this. One is the deployable lugs were removed and fixed lugs were added because we had a bigger volume. The payload mass also could be a little more better, and many other features that enabled LVM-3 to have this launch possible. And with the two modules, the lander and of course, the orbital module, which was having experiments at that time. So the rover, orbiter, lander, and rover were the three constituent elements of this mission. And the most important part is that we had a beautiful camera on board Chandrayaan-2, the high resolution camera, which gave fantastic images, reasonably high resolution. And we have the full map of the moon today, and that helped us in a big manner while planning Chandrayaan-3 mission. So let us look at the images from the Chandrayaan-2 orbiter, which is we had the L-band synthetic aperture radar, also the optical images, and the radar also gave beautiful pictures of the craters which are hidden below the surface, and also the hidden under the lunar regolith, which is the soft material. And this is one of the sharpest ever images that you have today. From compared to many other international images, the OHRC images of Chandrayaan-3, which was used for planning of the mission and the landing site, planning the avoidance maneuver, that is the crater and the boulders avoidance maneuvers. All that planning happened because of the planning happened because of the image availability for using our own camera system. Possibly some of you may be well aware of what happened during Chandrayaan-2 lander, and you would have studied this while following Chandrayaan-3 mission. So very important thing is that the mission up to the lander reaching the moon orbit at the designated orbit before its soft landing has been done perfectly up to that point. So there were no issues, but the issues happened only in the last phase of the landing, where we had something called the camera coasting phase, where large dispersions came into the system and the engine was not in a position to achieve the required landing conditions. So if you look back, then essentially there were many small problems which cumulatively led to the failure. So I'm not going to discuss that issue of how it couldn't land. But the only point which I want to tell you is that our ability to understand that issue has been so important. So all of you know that how to recreate a scenario while a space mission fails, and then understand the essence of that problem and take corrective action. I think that part should be congratulated. And we had many small issues that came up, which included the flow control valve improvement, which came very late part of it only. We could understand there were some issues within the regulation, throttling control of the engine regulation system. That was revealed only very short time before the Chandrayaan-3 mission. We could do that correction and implement. And also the instantaneous thrust regulation logic implementation, which was so crucial for achieving the stable propulsion and prevent the issues what happened in Chandrayaan-2. The bigger issue was that robustness development in the whole mission to handle wider dispersions. I think this is so crucial for any space mission. Possibly you understand that though everything we wanted to be nominal, it will never happen to be nominal due to various reasons. Our ability to plan for wider dispersions and engineer the whole system to handle this is so crucial in any space mission. Though it may not happen, it all happened today. Chandrayaan-3, it was mostly nominal. Ultimately, when it was landed, then there were other small things which we had to do, like the improvements in the guidance schemes, the ability to retarget in case of problems, the emergency situations, sensor failures, how to handle them. There were many such corrective actions we did, which ultimately led to the success of this mission. So it all came from the understanding what went wrong with the Chandrayaan-2 soft landing process. Now, once you understand that, there were many points that went into the definition of the configuration of the Chandrayaan-3. Of course, the heritage of the Chandrayaan-2 was well used, like the propulsion system, the architecture of the craft. Many things were used, the sensors, avionics, etc. So, but there were many improvements. For example, the robustness and also testing that happened subsequently is something which I would like to explain to you. Because the whole of this design changes which happened from Chandrayaan to Chandrayaan-3 should be validated in ground. This was a very important step that was decided. A lot of tests were planned, and from every test I can tell you that there were so much of information that came into the design, improvements in software, algorithm, and also the approaches that we went for the validation of the design, including the dispersion handling and failure handling issues. I think that gave such an input. In fact, possibly you may not know that the whole launch and the landing was planned much ahead of that dates that actually happened. But when we delayed it intentionally to ensure that all tests are completed to satisfaction and all design improvements are confirmed by the process of review that happens regularly in ISRO, I think that gave us the confidence to go ahead with this mission very positively. And the return to moon, I think you know that the whole purpose of Chandrayaan-3 was similar to what Chandrayaan-2, to demonstrate the safe and soft landing on the moon surface and demonstrate the rover moving on it, and also to conduct the in-situ experiments. I think we must be very happy to say that all of these objectives were successfully met, and we were able to achieve it. So before I go further, let me look at the whole the timeline that went into the Chandrayaan-3 program. The launch happened on 14th of July. So that I told you earlier that the M4 mission was destined to launch much earlier, but then we made it delayed basically to ensure that the whole test program of the Chandrayaan-3 was satisfactorily completed and all changes have been incorporated in the design. But while after this, then we were looking at the windows of opportunity to go to moon. Their window was getting very limited. So we had to reach it up to this point, almost reached the end of the window. Then the whole approach of reaching up to the moon is similar to what we did in Chandrayaan-2. Have the multiple Earth burns, then raise orbit, then move over to the trans-lunar injection, then reach the moon, and then go through the orbital size reduction by the moon burns of multiple burns, and then enter into the required orbit of 30 kilometers. So this approach was as we followed in the earlier sequence. The 5th August was the lunar insertion, and the 17th August the lander separation, and 23rd was the designated date for landing on the moon. Because these dates are very important, because the 23rd August becomes maybe the second day of the day on the moon, and we wanted this happen only on the opening of the window of the day of the moon, so that we will have enough of days available, Earth days available to conduct experiments on the moon until the solar light is available, so that the power can be generated. So this were very crucial. We couldn't shift these dates. So all this happened appropriately, and the whole mission planning went flawlessly. And also very important point for us is availability of ground stations. So this will explain later that we have the Bangalore, we have ground station, and we had support from other agencies like the JPL as well as ESA to support us in terms of getting access to the satellite data. Unless we have this data, we cannot do any operations. So the continuity of this observation was so crucial. In fact, the entire Earth burns and moon burns were done with the guarantee of availability of these ground stations to us. And the overall Chandrayaan-2 is, we said that there were certain changes from Chandrayaan-2 to 3. The propulsion module, we call it, earlier it was called orbital module. And it is now not having any major experiments as we did in Chandrayaan-2. The orbital module of Chandrayaan-2 is still functioning in the orbit around the moon. So there was no need to have the experiments. So it helped us to make a little more mass movement from the propulsion module to the lander module and make it more rugged. So similarly, the rover remained the same. So the mass of the lander increased, and hence there were major changes in the lander, including the leg strengthening, the engine reduction, the propellant tank becoming bigger, more quantity of propellant, etc. Including power capacity, the solar panel was made bigger, and all such changes were done to make the mission much more rugged. But the instruments on board the lander and the rover were remaining the same. So they were just the same, the 5 of those instruments. But we added more sensors in the lander for guaranteeing failure tolerances in case of mission. One of them is called the laser Doppler velocimeter, which was developed in LEO's, the Laboratory for Electro-Optic System, which was introduced in this mission. So the overall architecture of the Chandrayaan-3 looks slightly different from Chandrayaan-2. To talk about the major changes, I must tell you that it improved the number of engines which were used for lander. Earlier there were 5 engines, now we had only 4 engines. So you'll wonder why, when the mass increased, engines numbers came down. The reason is that in the with a lesser mass, we could have landed with a single engine at the center, but with the more mass, with only with 2 engines we could land. So there was no need of the central engine. So that was deleted, which helped in saving some mass, so that we can apportion that mass for more propellant and other hardwares which are coming in. The lander legs became stronger. There were improved sensors for navigation. The software was improved, and the solar power generation, the panels were added not only at one phase, it was added at multiple phases, because there is a risk of the lander not being oriented properly, facing the sun. If it happens, then the whole mission is gone. So there were additional solar panels added. So these type of improvements really guaranteed any such anomalies that will have to be looked at. And more importantly, we had enhanced simulation ground test to guarantee more safety on the mission. The special test and simulations were so important. So terminology is like called cold test, hot test, and drop test. The cold test were there where the whole craft is not in the final phase, but put inside in a distributed manner inside a helicopter, flown on top of terrains and conducted measurements. The integrated hot test is where the whole propulsion part is put along with some of the electronics and sensors in a lesser mass, lesser propellant quantity configuration, so that the mass and thrust can be balanced by counterweight system. And lander top test were testing the lander leg for increased ruggedness. And there were many other simulation test beds, including 6-degree autonomous simulation, software and loop simulation, hardware and simulation. And I can tell you all these test beds were so crucial during the even actual landing day. Many of the commands were sent back to this simulation test beds. It's verified, and after verification, only the actual loading into the real mission happened. So these test beds were live. Actual once Chandrayaan was running in the ground while the whole mission was actually happening in space. So just some of the photographs of those tests, which is very important and very interesting to understand. So to validate the performance of sensors, so what are those sensors we are discussing? The sensors here are the sensors to find out the inertial measurements, which are typical inertial sensors, the radar altimeters, the optical camera systems, which looks at the imaging, the laser altimeters, the laser Doppler velocimeters. So all these were part of the sensor suite, and they had to be working in unison with the computational system. And these were flown on simulated test beds or terrains where the measurements were taken, and the impact of the measurements on the overall accuracy of the whole mission was evaluated. And I can tell you there were so much of findings out of this tests where so much of corrections and improvements need to be done. I have some test videos. I do not know whether it will appear to you while it is being played.
IoT was conceived to validate integrated performance of all sensors, NGC hardware and software algorithms. A Mi-17 helicopter was used for ICT to test sensors for its entire operation regime, including hovering at 1.3 kilometers, 800 meters, and 150 meters, and lower altitude tests up to 10 meters altitude, which couldn't be done in LSPT during Chandrayaan-2 due to limitation of aircraft operating range. The tests were done at Chitradurga, wherein a special test site with simulated lunar craters were created to simulate landing site. 25 hours of flying time was used to conduct several tests with different combinations of sensors. The outcome of ICT provided several takeaways to fine-tune sensor parameters. The successful conduct of integrated cold test has provided greater confidence in the performance of all the onboard sensors and associated navigation algorithms. Integrated performance of all sensors and NGC was evaluated under engine firing condition for the first time in IHT. A set of dry run tests, static tests, closed loop tests, deboost and compact mission profile tests were conducted as part of IHT. Hovering and vertical descent of lander is demonstrated in IHT, and this has enabled successful validation of closed loop performance of all sensors, propulsion system, navigation, guidance, and control algorithms. Performance of optical cameras and 3D output of LHDAC is also validated in these tests. The test was conducted at SDSE Shah, which provided a benign weather condition in comparison to Chandrayaan-2 LAPT test site. Simulated lunar craters were created for IHT-2 for LHDAC performance evaluation. The successful conduct of IHT has provided great confidence in the overall system. Improved design of lander legs was validated through a series of drop tests starting from component level to integrated simulator and QM structure level, with different touchdown conditions such as on hard surface, soft surface, flat bed, 12-degree slope bed, simulating different combinations of vertical velocity and horizontal velocity. A new facility was realized at URSC to have a 11-meter by 7-meter test bed with flat and inclined drop surface. Lunar simulated soils were used as contact media for drop tests.
So I believe that you would have got some idea about the video was running well. So the type of tests were not in small numbers, they were in summing up to hundreds. Now coming to the Vikram lander. The Vikram lander was designed for surviving on one lunar day, the 14 Earth days, with this mass and power. And as you know, it has not made any major change compared to the Vikram lander earlier, but there were subtle changes as we mentioned in terms of the propellant, the tank gauges, the volume, the leg, the electronics, the redundancy management, the sensors, cameras, etc. Now, but the Pragyan rover was more or less the same. It had two payloads as well as the mobility, the power generation capacity, etc. So this was like what we did for the Chandrayaan-2 timeframe. Now the launcher, when you came for the Chandrayaan-3 mission, the payload mass was more or less the same. The injection condition was same, but we put a requirement, unlike the last time, that it has to be injected into the precise orbit of what was defined to it. And the vehicle did exactly the same. So I'm not going into that aspect of it, which actually helped the whole planning of the mission to be done very, very safely. So this was the launch. The first we had the earthbound orbit, and then further phases of earthbound maneuvers, which increase the orbit up to the lunar transfer trajectory, reaching up to the capturing on the moon, and then the second phase of the capturing on the moon, the deboost as well as the reaching on the orbit, which is the 100-kilometer, and later going to a lower orbit before landing process. So this typically, I think all of you would have heard about it and known about it, so I won't explain that. And there were many such burns, and all of them were executed very precisely in the planned manner. That we had no problems of any of such targets which were originally intended and achieved. Of course, there were small things which required corrections that were done both in lunar as well as earthbound operations. And finally, the decision for the propulsion module, lander module separation on August 17th, and also the planning for landing on 23rd, everything went well. I think I would like also to add at this moment, before we do the final maneuver of landing from 100 kilometers to 30 kilometers and then achieve a landing, we scheduled many testing on the engine systems and sensors. And this is very crucial. We've ensured that all of the engines are working nominally by conducting some test firing in the orbit of the moon, so that while we do the landing, the uncertainty levels are reduced. I think this was one of the important decisions taken to ensure that guarantee the soft landing with certain engine combinations. And final landing process, of course, the rough braking, the altitude hold phase, the fine braking, and terminal descent phase. The whole of this was gone through so much of rigorous review in terms of the algorithms that are to be used, the sensors that are to play, the time that you have to spend in each of those times. The whole sequencing went through rigorous reviews and debates before we finalized, including many such cases like how do you really detect that it has touched down, what type of sensors we should take, and what alternate options in case of failure of some sensors are happening. I think all of this went through very rigorous reviews and we had beautiful outcome, and I'm very happy that the whole review led to the success of this whole process. And ground station support was so crucial. The most important ground station which we depended on was our own ground station with a 32-meter diameter antenna at our deep space network at Bailalu. Also with the 18-meter antenna, which is available, 18.6-meter antenna. But along with our ISRO-based support systems spread across various places in the world, in addition to these two, like Lucknow, Port Blair, Mauritius, Biak, Brunei, we heard support from JPL as well as from ESA. There, Hawaii, JPL gives Hawaii and San Diego support, and ESA gave from Kuru and Gunhili, which was so crucial for us to do many maneuvers and to get the data at the right time. So we thank them for that support, which was so crucial. And after landing, I think the landing that all of you would have watched and seen, so I don't want to go into that. But after soft landing, the most important part is that we were able to deploy the whole of the experiments very successfully and safely. The rover came out, though there was a little bit of delay and anxiety during that time of the rover coming out, but we could bring out the rover a little later than actually targeted. And the rover came out and also did beautiful maneuvers, moving almost 100 meters away from the vehicle, and also doing a lot of hazard avoidance maneuvers, making use of the images that were collected back and reprogramming from ground. I think this was so very important for future missions, ensuring communication, ensuring path planning, typically in a robotic missions of this nature. And for this, the crucial part is the radio frequency links that exist between various elements, the ground stations to the orbiter, ground station to the lander and the rover. I think possibly, the propulsion module was not part of the whole chain. We were making use of the Chandrayaan-2 orbiter, which was still functioning in the orbit as a primary route for such connection, and not the propulsion module. So this is very important. And so it's a first unique experiment where the previous mission hardware was used for this present mission to work successfully in terms of this type of activity. But we had a method by which even lander can communicate directly to the ground station as well in case it doesn't happen. So these contingencies were kept in mind. And it was operating in 2 bands, especially S-band and X-band, for various aspects of it, which I am not going to discuss. There were experiments which was planned. There are 6 experiments, 5 of them in the lander and the rover, and 1 in the propulsion module. The experiments on board in the lander, they were REMBA, which is a probe that looks at the charged particle concentration near the surface of the moon. Chaste, which is an experiment to do measurement of thermophysical properties of the lunar regolith. And ILSA is an experiment to look at the vibration, or rather the seismic activity that is taking place on the surface of the moon. In terms of the elemental composition measurements, there were 2 experiments called APEX, APXS, which is alpha particle X-ray spectrometer, and LIPS, which is the laser-induced breakdown spectrometer. These 2 were part of the rover, where the first experiment was using an alpha particle, create an X-ray spectroscopy, and then measure the elements. Whereas in laser, there was a laser-based breakdown of the elements and then do the spectroscopy. So both these instruments were deployed and it worked very well, and we had beautiful data, which I will explain later. On the propulsion module, we had a payload called spectropolarimetry habitable planet Earth, which is nothing but looking at the Earth from the moon orbit and then measure certain spectral polarimetry characteristics and signature of a planet, which has a living nature. So this will measure more in terms of the infrared region, so that it understands and creates some database for which, if you look at possible exosolar planets, we can make some sense out of it, the measurements. So some of the important measurements is the chaste, which is actually the temperature profile in the lunar logarithm after probing into the surface of the depth of it. So the sensor measured very beautiful data, which showed the temperature variation from the surface over to the depth, which is very different from that we originally thought. So the temperature profile at different depths of the lunar surface is also shown here. Similarly, the time variation of the temperature by the different temperature sensors in the probe is also measured. So possibly good quantification of thermophysical properties are currently available from these measurements. And we could actually do this at 2 locations. I think this is also important, which we'll discuss later. In the elemental composition or using the LIPS, it is again one of the important measurements that we got, the first ever in situ measurements. And it also made the presence of the sulfur in the region without any doubt. And also we had preliminary measurements available for various other elemental composition. I think possibly, this type of confirmation measurements will take long time because we need to validate the whole measurements using other samples that experiments were done in ground. So all this data is now collected at multiple locations, and this will be used for further data research outcome, which is currently going on at different scientist level. Similarly, at APXS also did the spectra of the lunar samples. It also showed most of the major elements, and there are several minor elements using the spectroscopy. And this is also collected at multiple locations on the moon surface. The REMBA that which actually made the near surface plasma measurements, which is again very first ever measurements of the near surface lunar plasma. It says that the initial measurement showed that it is lower than what was originally expected. And this is again something very important and need to be understood in greater detail. Of course, we could see the deployment of the lunar, you can see a small shadow of the REMBA LP probe which is deployed in the background of the rover. So it's very important that the measurement could be done safely. Similarly, the ILSA, the seismic measurement package, which is again a three-axis MEMS-based sensor, which is deployed by this, which is again dropped from the rover on the surface of the moon. And this was again measured a lot of data in various events. It measured the activities which are taking place, including the rover movements and payload activities, and also Chandrayaan activity like the natural events. So of course, on this, a lot of studies and analysis need to be done. There are a large number of events recorded in the whole process, and this will be further studied and results will come out. So between Chandrayaan-2 to Chandrayaan-3, the most important thing is now we had in Chandrayaan-2 mostly a remote sensing set of measurements, but in situ measurement happened in Chandrayaan-3. This is very important. And of course, the correlation between our earlier measurements and now the present measurements is something that is going to be the most important part. For example, the complementary observations that are happening from earlier remote sensing experiments to the in situ measurements using REMBA. Similarly, the ground truth on the elemental composition, which is happening. Earlier, we had the space-based measurements in the elemental composition using class and XSM. Now we have the apex and LIBS, which will give a complementary ground truth of this. Similarly, the X-phosphoric neutral composition measurements, neutral to plasma connection, and also the SAR imaging and subsurface hydration, surface roughness, which is a water measurements. That part is not fully measured using our in situ measurements, of course. Of course, the Chastain thermophysical properties of the regolith gave a different type of data sets, which would be correlated with the other remote sensing measurements, maybe through scientific assessment later, which we have to wait and see. Then I believe that one of the important challenge was in looking at what we can do with this lander and rover further. So when we decided that we will do a HOPE experiments, that means the lander will once again do an approach to take off from the moon surface and then once again land. Once we decided that we are going to do it, there were many issues. For example, we have to bring back everything. The ramp has to be folded back. With the deployed ramp, it cannot once again lift off. So we have to bring back the ramp. We never originally wanted that to happen, but still we did it and worked well. So the ramp was brought back, the ILSA was withdrawn and back. So all of that was done. Then we decided to fire the engine and then see whether it will lift off and then move to a little different location. And we were very happy to see that the HOPE experiment succeeded. But we wanted to do more. But in view of the fear of any toppling and causing problem for the entire lander, we didn't do further because we wanted this lander to wait for next 14 days to come back to life. Of course, it didn't happen. But with that hope only that the whole HOPE experiment was not extended for longer duration or more distances. But at least we have the algorithm on how to do it and demonstrate it for a short liftoff. So this is something very interesting and which gives us confidence to have a reprogramming and planning of activities in remote space domain, which is very important for future exploration missions. Equally important was the recently announced propulsion module return to Earth mission. You would have known that the propulsion module, which was orbiting the moon, has now come back to an orbit around Earth. But this is also was not an easy task. After understanding the whole mission objectives has been fully met, the propulsion module is now around the moon and doing only one function called the shape payload, being observing Earth for that data. So we thought that why don't we use this for some more evaluation? And we had about 100 kilogram propellant left out, and we did a whole mission study on 100 kilogram was just not enough to bring it back to Earth. But then using a long duration gravity assisted planning of this trajectory, we could achieve it over a long period of time, not then the very initial firing, which is the first maneuver taking it up to a higher orbit. The second maneuver slowly taking back to the Earth arrival trajectory over a period of time, assisted by the gravity fields of Earth and Moon appropriately acting on it. So this is something very unique, and we could bring it back to an Earth orbit, which is a very big orbit, of course. but then it guarantees that it doesn't collide with any of the geostationary satellite at 36,000 kilometers and doesn't go back to land on the moon at the end of its life. So the debris falling on moon is also avoided. So once, if at all it becomes a debris, it will only burn out in the surface of on Earth only. So mathematically, I think that the team gained in a big manner in way of understanding and planning such a trajectory. So this also has been a very unique experiment, gives us a lot of confidence in the future. So I would like to conclude telling that the whole Chandrayaan-3 mission, in terms of its overall understanding of the problems that we faced in Chandrayaan-2, the learning up to Chandrayaan-3, the planning of the whole mission, and doing things far beyond that we expected. I think this is something very unique. And all of the experiments in the Chandrayaan-3 gave huge amount of data. And I have been behind the scientists who are looking at this data to come out with its own scientific findings and publications. Typically in such activities, it will take some more time to synthesize the data and generate good publications. And I am hoping that the whole activity is currently happening with all the scientists will lead to a very good level of publications in the coming days to understand the planetary science related to moon, which is so crucial for us in conducting further experiments. So I would like to conclude, say that the Chandrayaan-3 has captured Chandrayaan-2 also. The Chandrayaan-2 landing location also has been captured by the Chandrayaan-3. So it has been a beautiful view that we got. And we also want to thank all those participants and contributors, including international engagements and Indian companies led to the support of achieving this mission. Of course, I don't want to specifically thank ISRO, the leadership, especially my project directors, the center directors who actually worked hard in so many years, last 4 years plus, to make this happen. I think their contributions are so unique and very, very involved. And I should also thank the seniors who worked with us in reviewing and understanding the whole problem and then bring out and guided us in achieving the successful mission is something which I should thank from my bottom of my heart. But while we celebrate all of this success of Chandrayaan-3, big demand is already in front of us in terms of achieving the successful future missions of Chandrayaan. So we are in the work of planning Chandrayaan-4 and beyond, and also in terms of planning our missions to land human being on the moon, extending the Gaganyaan program, as well as building space stations. So all these new assignments and new visions we got primarily from the success that we achieved in Chandrayaan-3, the missions like Aditya L1 and the Gaganyaan that we could showcase in a very short period of time. So specifically, I should thank the entire Department of Space and ISRO community for coming out with so successfully overcoming many challenges and failures in the past to the glory that we have today. So I would like to specifically thank INAE for giving me this opportunity to present some of the outcome of Chandrayaan-3 and the results that came out of this mission. Thank you so much.
Okay, thank you very much, Somanath. It was an excellent exposition of Chandrayaan-3 technologies, the journey from Earth to Moon, and the critical period of 20 minutes operation of soft landing, then also the sensors that are used for various activities, the changes made from Chandrayaan-2 to Chandrayaan-3 to achieve the success, as well the various payloads that have been used, and also you are able to flash the results thereon from various different payloads. And on the whole, I think it's a grand success. Give him a very big applause for this excellent exposition. INAE is extremely happy to get the full details within 1 hour. I think almost 40 days journey has been covered in just 1 hour. It's not an easy task, but then you have made it so easy and we are able to understand. Thank you once again, and thank you very much.
Thank you, sir. Thank you so much.